So this morning I already talked briefly. We are going to try to study the protein internal domain motions in the solution. So I will not go to that point immediately. So on how to understand the data from there, but rather say from the experiment point of view, how do we plan the experiments? So that's something you need to think about it. Okay. So first that is you can say you haven't done the experiment, but I can tell you that the neutron spin echo is a slow measurement. A slow measurement is that anything you can do to improve the signal intensity to shorten your measurement time, it's important. So usually that means that your sample try to has strong scattering intensity. So how do I know that? Usually could do some other experiment. Just Laura is morning mentioned, don't go to neutron spin echo immediately. Try to do some sense measurements. Usually that help you. So try to do it.
Yeah, if you're lucky and you get beam time awarded by the SRC, but it might not help you that much. You might waste your sample and the beam time and my time and everything just to realize that, oh, I don't know what I'm doing. Yeah.
So no matter what, in order to study dynamics, it's always good to have structural information. Try to get some idea, either theoretical prediction, calculation, or better to be some experiment. If you have some sense measurement ahead of time, then what this sense measurement tell you that is usually as a function of Q and the scatter intensity with absolute intensity, you know that how strong your sample may scatter and how close they are to the incoherent background. Usually, how close to incoherent background determines that the highest Q value should go. Because if you are interested in the coherent signal, when you're getting close to incoherent background, odds are you are fighting against your background, fighting against your noise level. It's not you are not going to gain too much. So you try to stay away from here. So this is determined basically Q range, high Q range you can determine. You get some structure information. And for the low Q part, usually people say as low Q as reasonably achievable, but unfortunately that most of the most neutron spin echo instrument, the lowest Q they reach is about 0.05 inverse electron. You can push it to 0.03, a little bit lower, but that's about the low Q limit. So the low Q is pretty much determined by the instrument, but high Q is determined by your signal to noise ratio. When noise here, we're talking about incoherent scattering. So that's the first thing. Okay, gather some structure information. Now, second part is think about your sample. So when come prepare sample, how do we improve the scattering intensity? For Smango neutron scattering, people haven't studied, but naively you can think about increased concentration will help, right? If you can increase the concentration, that's always a good thing. Okay, but there's a limit you can increase your concentration because if concentration too high, sometimes that's changing the way the science you want to study. You cannot change that, right? And another thing you could think about by making sample thicker. A thick sample may not always help. And this is because it is not a full semester class I need to teach, so I cannot tell you how to estimate that. But if your sample does not attenuate the neutron too much, sometimes make thicker sample is useful. Roshin, for example, for your experiment, what's the thickness you used for the 2 millimeters? So instead of 1 millimeter with 2 millimeter to improve. And if you ask Laura, say, if you can use a 4 millimeter, even better. Which I agree, but usually then your amount of sample, can you afford that? That's a different story, right? And so usually thick sample, as long as you do not introduce multiple scattering, the people asked a good question this morning, and try to avoid multiple scattering. As long as you do not introduce multiple scattering, thick sample. So a few things like concentration can help you, and sample thickness. This will help overall improve scattering intensity. Okay? Yeah. So now come to the measurement. So this is something you should discuss with your instrument scientist when you design your experiment. I mean, you particularly they will ask you, do you have this data? If you have this data, it really helps a lot. Okay, and then you will discuss what the sample environment should use, what concentration. Okay, so now come to the measurement. So to the neutron spin echo measurement, usually you need to think about what Q range you like, and that's. But then you see that even though our detector is an area detector, they can cover certain Q range, but they cannot cover all the Q range you want to get. So you may move the detector several times to cover all the Q range you want to reach, because this is the size of area detector. They only cover a certain angle. The Q range is related to scattering angle, and you need to move them if you go to high enough Q range. For example, for Rorschach experiment, you use the 3 configuration. 3.
Yes.
I think you use the 3. Okay. So that, but if you need to use 3 configuration, means that you will increase your counting time, right? Because instead of one position, you count everything. Now you need to move things for the same condition. You need to repeat. So you need to have measurement angles, Q range. That's okay. Measurement configurations. Okay. So then you measure your sample. Usually you are interested in the protein inside, right? But your sample have something else in addition to your protein. There are something else, right? So the buffers, they have signals. You need to correct them. You need to measure the buffers. That's important. Okay, because you need to correct the buffer, the dynamics. Okay. And another thing that at the beginning of the experiment, you need to measure your resolution function. Okay. And usually they use something that will never decay. For example, carbon, black carbon or some powder carbons, and they do the resolution function measurement. So those are all needed. But usually for one experiment, once you determine the measurement configuration, and then use the resolution function, you measure it once for your whole experiment. You just repeat the simple and buffer conditions. Okay. So far, any questions? And then once you measure all of them, you need to go through the data reduction to get, in the end, that you will get your intermediate scattering function. If you get this data, then you're on your own. Well, not really on your own. You can still ask Neutron Center to ask help. Okay. And but if you know what to do, you can start to model your data. So that's basically for experiment. That's a procedure you're following. Okay. Yeah. So for each measurement, once you start to measure that, then you will realize that the measurement for neutron spin echo is very slow. Why? So remember that for each Fourier time, we'll need to one measurement, right? For each Fourier time, we need to have 19 points, phase points. They have like I believe it's 5, because 3 up and 2 down, 5 up and down measurements. You don't need to worry about. So for each Fourier time, you need to do this. But for each Q value, for one Q value, there are many Fourier time, right? You have many Fourier time. You say I want to measure the 1 nanosecond, 5 nanoseconds, 10 nanoseconds, 20, 50, 100. Each of them is a measurement. Okay? So, and for each Fourier time, you already have 24 points. And that's for one Q, but you have multiple Q, right? Q values. Okay, say you need 3 configuration for that. Look at how many points. Let's say 1, 2, 3, 4, 5, 6. There's very few points. Usually we do like 12 to 20 points here. Let's say 12 multiplied by 3, 36. Multiply, say 20. That's 720 measurements already. That's why neutron spin echo measurement is very slow. You need to measure many things. Okay, yeah. Okay.
And multiple concentrations.
well, I mean, the rest of your simple design, I'm just give you an idea. So the measurement is common that take days long for one sample to be finished. Just have an idea. Doesn't mean that you cannot design a smarter experiments to correct that, but that's for the special experiments. Usually for the typical measurement, if you go through this routine, it's common to take days to finish one sample at one condition. Okay. So any questions? That's basically, I just quickly show you that as a user myself, if I go to a place to do experiment, this is something I need to think about and talk with the instrument scientist in order to design the experiments. Okay. Any other questions? Okay. So for protein in the solution, usually when we measure the neutron spin echo experiment, most of the time, particularly in protein solution, it's exponential decay, the function. I'll explain later why it looks exponential decay, but I want you go through to try to start to get an idea for that. So exponential decay, basically, we can fit exponential function. So a lot of things follow the exponential decay. And so people did the dynamic light scattering. And can you give an example? What type of the motions give exponential decay for intermediate scattering function? Protein diffusion in solution, right? Yeah. So for the protein inside the solution, usually basically the d0 q squared times t. That's a simple. Then my a basically equal to d0 times q squared. If I know my q, I can know my d0. Okay. Okay. Yeah. So if I have a single protein, I can measure neutron spin echo. That's the intermediate function looks like. So then immediately you realize one thing. This function time, intermediate scattering function. So if I take a log scale, if I take a log I of qt, then this is just a q squared t. That's just a linear function, right? So start with 0 in log scale. And the different q values, that decay will be different. So now the question is, which one is the low q value, which one is the high q values for this curve?
The fastest one.
The fastest one is
yeah, this is a high q value because that this is much bigger, right? And this is a large q value. This is small q value. Okay. So that makes sense. But they describe same type of motion. The reason they decay faster doesn't mean that there's a different type of motion in the system. It's just simply that there's a q dependence in terms of the decay curve. That's coded by my q values. The larger q I go, then they amplify whatever small motions you have in your system. Okay, so I will talk about later why is it like that. But this is a common. I mean, of course, in the simple diffusion case, I can write this down. But even for other polymer, other case, generically speaking, typically, not always, and that is small q. Typically, the relaxation time, the decay time you look at, it's basically smaller, and larger q goes faster. So that means that if you plot out the decay rate, which is a decay rate, as a function of q, they follow this one. Because a is d0 times q squared, right? So the larger q go, the faster it decays. That's why it decay more and more, okay? But typically, in order to get the diffusion coefficient, we take a divided by q squared. Then as a function q, if it's a simple diffusion, That should be straight line.
Yes, makes sense.
For spherical particle, dilute condition, if you calculate diffusion coefficient, it's a straight line. Okay. But this is not the case if your particle not spherical particle. When it's measured by the neutron spin echo, and it's become complicated. But what do? We still assume that it simply follow this function. But now we call it d effective Q times Q squared times T. The difference that we get a decay constant A divided by Q squared, then this value may not be constant. It may be constant, but it may not be constant. Then they may have some interesting Q dependence. That's called D effective. They have some dependence here. Okay. Then this is something we'll try to figure out. Okay. So without going through the details, well, assuming that we already have experiments measured, then we try to get the D effective Q. Okay. So I'll give you some data. You will try to fit that, get this, and compare to our some theoretical calculation. Nora will show you tomorrow, and I'll give you some data from simulation and to see what's the difference. Okay. So for the rest, we try to extract information from experiment data. Any questions? No? Okay. So just like this morning when I showed the talk there, this is the data Roshin and Janet, the previous student, collected for the NIST map. We try to fit that with this function to get the effective diffusion coefficient. The data I give to you, I think this with different concentrations, right? And what we're trying to do, did you get a chance to read the handout? It's a lot for the lecture notes there. So we try to get this one and then eventually to linear project that to infinite dilute conditions. And can you erase that board? Because I can show that to them. So, but before we start analyze data, I want to show you how if you finish your experiments at the NCR, neutron spin echo, then you can know their file called all echo file. This is one of the experiments. You can see that. And you can see this is the phase point. They have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 16, 17, 18, 19. Yeah, I'm right. So they have 19 phase points. By fitting with the cosine function, then they get the amplitude term out of that. And that's what you get for your intermediate scattering function for that. And then you see that how they change in the Fourier time, they change the magnetic field. So this is the Fourier time. This is the 0.14 nanoseconds. And then the 0.24, you can see how they change over Fourier time. They decay more and more than 1.5, then eventually 4.979 seconds, you see. Then eventually it decays. Then when you intensity getting close to background, you have nothing there. You cannot see too much now. So that's basically the scattering. So that's the different Fourier time. They have so-called up and down. That means that is without the simple insight, what's the total polarization you need to do normalization. This measurement up and down is for normalization purpose. Okay, yeah. So that gives you a flavor that this is a different Fourier time, how the data looks like. We try to get amplitude. Clearly you can see that here the amplitude is larger compared to larger Fourier time, right? So that means that my signal anyway is decaying. Okay, so here you see that I have the buffer, that's my background measurement. And then I have this one. Okay, that's a buffer. I should have the resolution function somewhere. Okay, carbon black. That's my resolution function. If you look at the resolution, you see this data is much better than my symbols because the orange looks good. Because they should not have too much decay. So have a little bit decay that's intrinsically related to the homogeneous of magnetic field. That's why it's called the resolution function. Okay, but overall that the echo looks pretty good for the resolution function. And then these are proteins. They are not they're okay, but when you go to higher fray time, they're not so good. Just give you an idea. If you look at the buffer, my buffer almost have nothing inside. And even at the beginning, there's not too much echo there. If you're going on, it's basic noise level, okay? That's the buffer. So that's give you an idea how the data looks like. Any questions so far for the data? So once you get your data here, then you can use this one to determine the phase point for different one, and then reduce the data to FQT. Usually, every time you come here, you don't need to worry about it. Every time you come here, Instrument Center will show you how to correct this, how to reduce the data, get an intermediate scattering function. And so in the end of that, then you will get the so-called FQT. You can calculate the FQT out of this. And if, okay, I don't know if all the number I put it there correctly, simple transmission, assuming it's correct, then they give you FQT. So they already determined the three, basically Q. They use this one, you see the blue curve, that's the Q they use. They use the 3Q value here. Okay, then you have FQT decay. This is the T in terms of the nanoseconds. This is the normalized intermediate scattering function. Theoretically, at 0 seconds, it should start with 1. Okay, any questions? But this one, Instrument Center will show you how to go through that. That's why I just give you a flavor, show you how it looks like. I will not go through this. Any questions? Good. So now, assuming that you know how to reduce data, you already have the FQT from your experiment. So, all right, this is our data reduction software. Okay. So, okay. Yeah, I'll minimize this one. Okay. So now you already have your data. So the way you analyze that, you go to analysis. I'll ask you to use the peak fitting. Okay, that's what you need. Okay. So if you look at the folders,
Superconducting coils, we should be able to put the right sample.
there are 4 samples. We made 10 milligram per milliliter, 25 milligram per milliliter, because I already went through myself, just to make sure that everything's okay. So that's why I have many more files than you have. Okay. And so I would say divide and conquer, because we have 4 data set. We need to finish that. We need one person to summarize all the data set. And I have this one called a template already built for you. Once you calculate all the Q range, once you plug in the value for the decay constant and its error bars, then automatically it can calculate your diffusion results. And in the end, that you should be able to plot all of them out by putting to the diffusion coefficient everything. And this is the simulation result I'll give to you. And we have 5 people. I'll propose the following way. One person in charge of the put everything together and plot. And the rest person, each one take one concentration to do. So how do you like to divide this? Who's the person summarize all the results? Who take it? I'll show you how to analyze the data. Okay.
I can make that.
You do with which one? You summarize all the results? Or you want to analyze one of them? We need to
Summarize all the results. I can do that. Or actually, I would prefer analyzing.
okay.
So I learn.
So you are do 10 milligram per milliliter. How about that? Who's going to take summarize all the results? I need one volunteer, and you guys decide. I don't want to assign this. Okay.
But they all need to learn how to analyze.
Yeah. Well, I mean, yeah. The one person can sit into. They can still do it, but I need someone volunteer in the end to summarize all the
No,
results.
I think what he's saying is each of us will do one concentration.
Yes, that's correct.
And then one person will collect all the data, understand. and then-
Yeah, I understand.
Yeah. So how about this? And so 10 you do 10 milligram per milliliter, 25,
Yes.
50, 100. You choose whatever concentration, but you are going to have the template and plug into final results. How about that?
Okay.
Nice.
Okay. So
Sounds
assign. Okay. Now I will use 10 milligram per milliliter as an example, but the rest you do your stuff. Okay. Okay. So to do here, you first said that you go to know the data called the Dave files, because I already saved. Because when you reduce data, you can save all the Dave files. And you click Dave files, and so I have here. Of course, for me, I'll choose 10 milligram per milliliter as the example. Okay.
I don't think my Dave looks the same as yours.
Okay.
Dave is different than your Dave.
Okay. It depends on it's possible. Yeah. So go to analysis 1D peak. Yeah. Everyone get a 1D. So let me starting from scratch. So you go to analysis, 1D peak called a pan analysis, peak analysis.
And then we do the underscore all.dave.
Not all, because somehow Dave has a problem. I saved all of them, but it's just one by one. So you go to node Dave, and and let me find out my place. So I can. You start with the lowest Q value, 0.06. Just double click it. That you will get data. Does everyone have the data now? Has the email reached your place yet? Okay, maybe because the file is.
Is it a little big? Yes.
Yeah. Did you get it? Probably in the end you need to have the template too. So, Aaron, did you get data?
I'm getting it now.
Okay.
Which one do I open?
You have data too, right? So how about you work on the one with 25? Because the same with what's your name again?
Sure.
Sure. Yeah. So because that you can catch up later. So he will work with the 25.
Sure.
Okay. Yeah. So now I think that every concentration someone is working on that now, right? So now you have this one. You can see that you can, because for this Q configuration we have actually just only. Actually, not this one here.
Am I just opening the 25 milligram all file?
No, just 0.05. Did everyone open the first configuration for the Q value? Then you should.
506.
Oh, you called it 0. That should be the same. Yeah. Let me see. Yeah, called it 0.06. Sorry, I was wrong. That's a mean value they chose to name that Dave file. You may need the template file later to have you already have template file too. Okay. Okay. Yeah.
Yeah, I don't know.
Yeah. So load the lowest Q value one. And if you look at here, they continue. They have a 3 Q range. Okay. 1, 2, 3. Okay. Yeah.
Yes, I don't know. Suddenly an issue with my Dave.
What happened?
Actually, it worked in my Windows. I think.
Your Dave.
I don't see it.
Can't be open.
Okay. Actually, it's there in my computer. Windows. This is Mac. It's not.
We worry about it later. You guys.
Yeah,
You just work with someone whose Dave is
I-
working.
I was also thinking.
Does
this
Dave
is
even
an-
works on Mac?
Should work.
Yes,
I
it is.
copy it. I don't know why it's not
Mac
there.
was from-
If you open the files, are you able to?
So I'm here.
Your Dave is working.
So the data's
Okay, I'll
here on
Yeah.
my
And I'll go back and do it in
laptop,
the
but
computer.
I can't get it. I can't access it from the Dave. It's not.
So
Do you
Erin,
want
what's
to
your
change
problem?
the file type?
I tried to.
Steve unzip it. It probably
Yeah,
might still be
or
zipped.
Yeah.
Is it still zipped when you
You
on
need
your?
to unzip it.
okay.
You need to
Yeah,
unzip it.
you
If you
have to
didn't
unzip
unzip
it
it, you
as
cannot access it.
Unzip the.
Just yeah.
So just go to your folder and hit unzip and extract all the files, and then it'll
Have
appear.
that in the file explorer.
Okay, so this is how the window looks like, right? Yeah. And then how did you load the data?
That's already on.
You just
I
open.
think it's unzipped already.
Okay, then give a try to see if you can go to that folder.
So this is from the days.
Yeah,
And then I guess you have to
go
select
to
function.
analysis tool, analysis 1D, peak fitting.
Oh,
Pen.
0.065.
Oh, yours is different. It's the old version,
7.
but it's okay. Go to data,
data.
and load data file, and find the folder where you stored.
So you take the load, he said the lowest one.
And
Oh.
then 0.06 should load the 0.06.
Okay, I got it.
Okay. Okay. So first you need to define the function you like to use. Okay. You select function. Unfortunately, do not have it for exponential function. You need to have. You need to. I have already saved something. If you copy the mine, that's called exponential function. If not, you can type it here.
There's no exponential function?
That's the exponential function. P0 times exponential P1 times x. Just type that there.
How do I type one in if I don't have that?
You just define the user function. Go to select user function. Just select user function. Have you selected it?
User macro.
No user function.
Okay, so from this
Select function. Select user function.
So I
There's a
think
user
it's in
function.
this window.
Okay.
And
get
just
out
type
of
it.
that.
Oh, this one?
And then I think is it you have different Dave. Is it select 1D function?
Yeah, I'm in
Should be-
select
Yeah.
1D function.
Yeah, user function. select 1D function. Yeah.
Oh,
Yeah.
select 1D
And
function.
then
Then
user defined.
Yeah, user defined. User function.
Yeah,
Yeah.
I think that's what it is.
Okay.
Yeah.
And
Just
then
You have the same one, yeah? P0, P1.
yeah. This
Oh,
P0 is the
okay,
first
so
parameter. P1 is second
Just
parameter.
edit it to look like that.
Yep.
Yeah.
Go back and do it. So we don't waste time.
So you have it.
We have it. Wait.
Okay. Then make sure you save your expression because you keep using the same thing. Yeah. Just yeah. Put it into your folder. For example, in my folder, I call it exponential 1. Yeah. Yeah. You can save whatever you have.
So then save.
Yeah. Once you save it, just click accept. Okay. Accept. Take default value is fine because here you can define lower fitting boundary, upper fitting boundary, and all kinds of interesting. Just apply and
Accept.
dismiss.
Accept.
Yeah.
Just apply.
Apply it.
Yeah. Then you can say fit current group. Okay.
Oh, do I just accept? Do I just apply?
Yeah, apply and
fit
dismiss.
current.
Just accept everything.
Oh.
Then you
so
can fit
that
the current
fits
group.
it to whatever function that you define.
Yeah.
Right.
So
Okay.
then you can say that they give you fitting parameter and the error bars. Okay. And that where you need to put your, because that means that, okay, so this 0.05, you can say fit all groups. Okay, you just fit all groups, then they fit all the Q range will fit it, okay? And so then you can put it here, okay, I forgot which one I chose, the 10 milligram per milliliter, 0.05, I say the fitting parameter P1 is 1.282 E7. I try to put a number there, and the error bar is 3.818 E5. Yeah,
That's for P1. Why did you select P1, not P0?
P1 is my decay constant. Because remember the function we chose is minus P1 times x. X is my function t. P0 is the prefactor.
So P1 is.
Yeah, because if we plot there, then the diffusion will automatically calculate that's a 4.65 Armstrong square per nanosecond. Okay. This will take some time for them.
No, it's okay.
Yeah. Oh, you already have my values. delete the type it again.
They're
Because
very,
you will get your result.
they're very different.
Or this because this is P1, right?
They're not the same numbers.
So yeah, you're reporting P1 for
No, that's
units
diffusion.
case,
You need
which
the
is 10
diffusion
mgs per mil.
Oh yeah. So this is 10 mg per mil here, and then this
Yeah, they're
is
still different.
which value?
It's
goes here?
what's your concentration?
Oh, what's
You're,
oh what's
you're
the
working
difference
different
between here?
concentration, right?
25.
Or okay.
I don't know. I just don't understand. So this is P1, right?
Just look at your function
So
form.
this
Can you go back to
is-
select your function form?
So at Q.
The concentrations are
Q.
at the
So
top.
I'm just trying to
Just select
report.
function form.
How do I open mine?
No, okay,
So
just go
this
ahead.
is
Use the
P1
function.
value that you get from
And
the
restore.
right? And then this
Restore
is
the
P.
function. And did you save your?
I did.
Yes.
It was here.
Oh, P0.
No.
655.
So
You should
your
have it.
P1 is
I didn't say it.
This
DQ
is
square
maybe
is
save it
your
a different place.
relaxation time. Is I think. Is so the equation, what is it? P1, P0 and P1. P0 is
P0
the
times-
amplitude, or and the relaxation time is what? The diffusion is the P1.
It's P0
P0 is what?
times
P0, I think.
exponential P1.
I think P0 is that
Times X.
constant, and P1 is that exponent.
Yeah.
Yes.
All right.
So you're reporting P1 under your concentration.
Oh, so I was just doing his. I have the same. This is for the 10 milligram.
Oh, you're doing his.
I was
okay.
just. I'm gonna do it for
Yours is
mine,
different.
but
Yeah.
I'm just
Oh, okay,
Following
okay,
along.
okay.
Okay.
doing example.
So let's write this down.
So what's your concentration?
Oh,
Oh, so mine's the 100.
okay. So it's, I just
Yeah,
had to
100
go back to
milligram per
group
So
1.
then go back.
So where's the difference between the groups?
The
Data,
different Q range, you know,
Oh,
the Q
okay.
value. That's different Q range.
So that's for.
low data.
So then, if I want to go to my
Yeah, you,
concentration,
you can delete all of them and repopulate it with your
This is-
results. Leave
You
the
should
Q.
say
Oh,
leave the
you
Q.
should get all.
Oh,
to have
Leave
all
the
three of
Q.
them,
Yeah.
right?
That's the Q. The here is Q value.
Oh, yes.
And
you have
this is the
100. So
concentration.
move through. You have 1, 2. You have only one group.
Okay.
It's coming back.
You selected only one group.
So when I switch to the second
You have
group,
to
Oh.
load
If you want.
that's
I mean,
okay. So like,
would be then this one.
Yeah.
if you
No,
only
data
loaded
go
your
back, yeah.
concentration.
So there's only 3. What happens now?
Okay, then you analyze
So this
another
is for all-
configuration. Remember, we said that the different configuration.
You know what? Just select all of them. Like,
Because if you look
Oh.
at the echo,
press the control tab. Or
look
shift
at here,
grab
you have
all of them.
4 different configurations.
Oh, okay.
Then you can
I
go
see.
through all the configurations.
If you
Oh,
like click the
right.
top one
Click
and
the
then-
top one.
just once and then shift at the bottom
Oh, shift.
and hold down shift.
I don't know why it's not letting me.
That shift, hold the shift. And now
No, you
go
don't
to
delete.
the
You
last
don't
one.
keep the. Just only delete the numbers because I
it's not
already made
letting
the template. for
It
you.
doesn't let her.
Okay, so
Okay.
now you can
Okay. So
What's the difference between these ones?
now go to
Oh,
the
those I already
top one.
copy the
Click.
P0.
Uh-huh.
Just want to, just in case
Okay,
if something go
control.
wrong, I want to
Now
have
go
idea.
to the top bottom
So-
one.
Oh, weird.
Yeah. It has some setting.
Sorry for
Let's
that.
take them
Just
one
pick
by
your,
one.
Pick your concentration, whichever one you're supposed to.
So
Okay.
basically, you need to go through all the configuration, get all the Q value, and fill the template file for all the.
Slow down a little bit.
I just tell them what they need to do,
Yeah.
then I can slow down a little bit.
Who made this program? Who made Dave? Is that internal?
Sorry?
Is Dave an internal?
You have the free software. It's
one
developed
hour
internally.
process.
Yes.
I say because it's Excel compatible. Like if I copy this number, it'll just
Yeah.
it'll
It
actually
should-
be an
So
exponential,
no, you
Yeah.
still don't have.
which is surprising to me.
Yeah, I'm surprised because when I was working on that, I was typing myself. I didn't use this way. If I knew that, I would copy paste.
Yeah, because the first one I put in, it actually expanded, and I was like,
Yeah. Are you working on 10 milligram per milliliter or 25?
25.
Okay.
You need to-
It's working.
Take that one and save. If you select this and you save open.
So now do I just?
Then continue for finish
Okay,
your
so you
all
have to take
other
each concentration and load it because there's something corrupted
Then
in
you
that
need to
file.
select your function.
No, it doesn't.
Then you need to always restore. That's annoying part. And then if you save it
I
somewhere,
do save it. I don't know where it's going. Watch this. If I
Okay.
do this, and I type in.
So they go to like.
Okay.
It exists somewhere.
Okay.
I think it's
the
saving it to my
folder, different
OneDrive.
Folder, yeah, the different.
Close
info
this one
folder.
too, because it drives you crazy.
Yeah, accept. Just fit the current one and fit all the group.
Yeah. What is the next step again?
So each house
So it should be.
It's the fitting.
Uh-huh.
Have you get a model yet? No, you didn't
yeah,
get a model.
she did the
Data.
first configuration.
Oh.
But now she has to do the next
File.
one.
Okay, go to the first configuration. I didn't say the fitting. If you say the fit,
Oh, you closed it.
okay.
Just
She already
take
wrote the
that.
parameters.
Mhm.
It's Excel file.
Alright.
She's already written the first.
Yeah, okay, now you need to select function again, then go to select function.
so-
Unfortunately, whenever you
so-
load the build configuration, you need to do it
Then
again.
user-defined.
User function,
User
but this time you can use restore, yeah, and then where you
say-
save, can you find out where you save that exponential function? Yeah.
Great.
No, hold on, and then did
Fit
you,
all groups.
okay, then fit all group,
So now just.
yeah.
Nice.
So now this is
Um,
4.0.0.
Can you show how the equation is written?
Uh,
You can-
It's over there.
no, how you have it in your
That they have
Yeah.
explained.
Yeah.
So now
It is actually under curve 1 user function.
it's okay. Did you wrote it? Did you manage to write the equation?
This is a
So select one the function,
Yeah, this is
Oh,
the
user define, user function. All right, and
Okay.
P0 multiply
That's it,
So
right?
X
So now I'll
X.
work on my data.
okay.
minus P
Overwrite it, is it?
multiply with X.
Here.
Or save expression first so that you have a name it, give it a name exponential one.
It tells me this is damaged and can't be returned.
Okay, save. Press save. Awesome. Now say accept. Okay, leave the default value between 1 and 0, so apply. Okay, and now you go here and you say fit current group.
Okay. And then this.
And then
was
these are the P0 and the P1 that you have to put in the table.
Oh, okay.
And you need to do the same for all the other 3 queues.
Switch it off. Say like there's a.
So these are the different.
Okay, what I so you are not saying, you're saying that the software is fine, it's fine.
Okay.
Yeah, it's just that this one you can override because there should be a prompt in your security that.
Okay.
And if I turn it, but it looks like Bella does the same, so it's the same in all rooms. It's not like, but if I turn it off, it gets too hot. I like to see the cold. Yeah, it's cold.
Okay.
If you leave the window open, actually, I close it right now outside.
I'm at the 10th floor. I don't know if I can open it. Oh.
I don't think our window's
So I'll
open.
just say,
I don't think our window's open.
They open, they don't.
I
I
just say
think they
absolutely
open.
and I cannot put anything.
At the 10th floor, they wouldn't risk it. So.
Oh,
you're
I
set.
put it in wrong.
Does anyone
No, I
have data?
understand what you're saying. Like you can say that it has detected this.
Say
We're
hours.
trying.
Grab this guy.
Yes.
Yeah,
I remember
and-
Rebecca, what are your
and-
first
and-
2 lines?
And have it.
What are your first 2 lines?
But.
Like for the concentration for Q?
Yeah. Yeah, like what are your outputs?
Started talking this
Because you're doing 50.
about
Yeah.
something
Are they
that
1.22
plans to have
and
been
308?
just all
Yeah,
about
for the air.
with the
So like
visitors.
1D
And then I told him that I want to
user defined.
oh, but maybe we can all go like down in and visit, and there's gonna have somewhere there. It will be nicer. And then I don't know because I didn't talk to him. So
Yeah, no.
if no one wants
His
to,
idea of flying everything.
But anyway, it's.
Yeah, because I was thinking about it because last time when Derek Roshin took me to the restaurant you recommend, and we said we have to treat Nora with the best restaurant we can find in this area.
Okay, so is there anything after this? Just finish the
This area here, and I said, then you have to come to know you, because generation we know that perfect. Wow, you have a Japanese restaurant here. I said, yeah, we have the best one. I was teasing you. I was just teasing.
Everyone's happy so far?
What do you do after this?
Okay. After is
That's a good. It's a
is,
good idea.
coming to next step.
The guy.
对 I just try to make sure that everyone on the same page. So how much you have still try to finish? Anyone has a point that could pause a little bit? Okay.
So I've understood how to do it because
Yeah.
I've seen her interface.
Yeah. Okay.
I will go do it in my.
So there's someone finished, but take your time. I'm just saying that, so right now the diffusion coefficient you get is at a finite concentration. But we are interested in the internal motion. Actually, we are interested in the individual proteins. Ideally speaking, we want to infinitely dilute the condition to know basically the diffusion coefficient for that. But we can't do it because the infinite dilution, there's no signal, right? So how do we do that?
Extrapolate.
Exactly. For people who did the dynamic experiment, can you tell us what do you do get the infinite dilution diffusion coefficient?
I mean, I just extrapolate until like essentially.
You get the concentration, right?
Yeah.
And then do linear fitting and then infinite dilute. That's what we are going to do. So basically, I'll show you that this is right up. Send you guys.
So we are going to plot the diffusion coefficient as a function of concentration.
That's exactly what we need to do. So that's what we need to do here. Okay. So, thank you. Go ahead.
Concentration and it might look like this, and then since you have 0, but it's so
Yeah. That's the infinite dilute condition. Okay.
So we could also get like intrinsic viscosity and.
From the viscosity measurement as a function concentration, you get the intrinsic viscosity, but not for this one.
Not really.
So if we assume like for proteins, I mean we cannot if it's not a sphere.
You will get a so-called KD parameter for the slope. That's related with the second variable coefficient. That's interaction related. That's correct.
Fit that. Okay.
Yeah, that's a slope. But essentially, what do you need to do? Because I usually like normalize everything to D0, but before you normalize, you can just do a linear dependence concentration and fitting that. So which means that what do you need to do? Now I need people to propose, because we need to do it at each Q point as a function of concentration. Because for the light scattering, you only have one Q points, right?
Yes.
And also, light scattering go to such low Q and such small Q range, the diffusion coefficient is not going to change too much. But here, we need to do each Q point as a function of concentration. Now that's why then you need to, either you put into the Excel file, you can do the linear fitting in the Excel, because if you know how to do Excel, but I don't know Excel very well, I actually use David to do it. What I did is that I created a function by copying from you see that I have different concentration, a different Q value here. I plotted the concentration, and this is the diffusion coefficient, and this is the error bar. And I just load into Dave, then they fade it.
Yeah.
And you can do this way, but in this way, in Dave, you need to use a linear function to do that. And how do you define linear function? So I already have it. I can show you the function, how it looks like. I have linear function here. And it's very simple, P0 plus P1 times X. Okay. So after you finish your group of the concentration, you need to put them together into one spreadsheet file. Then you need to generate the concentration dependence for all the Q values.
how are you inputting your data? Oh, are you just pulling it from Excel?
Yes, just save as a text file and then load it. And then, okay, that's a very good question. So once you save that file in the div, you need to load it in a different way. So data, now you are inside the div file, you load the ASCII file. This is 3-column ASCII file. That's what you need to use. So for example, I already saved mine, so I can load like 0.05. Okay. This is the concentration dependent for my data. So do you see a problem here? If I want to use a linear function to fit it,
It's not very nice.
it's not linear.
It's actually nice.
So that means that this one concentration too high. We need to exclude this one out because that's linear extrapolation has to be go to low concentration enough. So only use first 3 data points. Okay, don't use this one because that. But you will find out that with some hierarchy value, actually it's not so bad to include this one. But we need to be consistent. If we decide to actually throw this one out, then we just use the first 3. Okay, and that's why I want to plot it out to let you take a look. And clearly, this is not linear dependence. Including this one doesn't make sense. So we should not have this one. So now, next step, once you have all the diffusion coefficient, then you need to extrapolate. But keep in mind that what you get just now is a decay constant. In the template file, Excel file give to you that can automatically calculate the diffusion coefficient for you. That's the second tab if you click that. So I already did my homework. So say for example here I already input the decay constant. That's give you diffusion coefficient here because I didn't do. In this template I didn't do other than everything else is 0. The unit is m square per nanosecond for this. Okay, and if you want to say after I finish everything, how does it look like? That's all the diffusion coefficient eventually you will get. Okay. So maybe some of you know Excel very well. You can directly use Excel to fit. Yeah.
If you can give me this data.
So if I have
Well,
this,
you're supposed to produce all the data. Yeah.
if I have my 25 concentration diffusion,
Yeah.
I take this and put it in this text file.
That's
No, but now you need other people at different concentration. Now you are doing concentration fitting.
So I need
so
all.
now these are the different
You need
concentrations.
at least the first 3 concentrations because we just showed the last concentration
No.
is will not be linear
So if you go here,
as a function of concentration. So you finish 25. Did people finish 10 yet? 10
no,
milligram?
my wave is not working.
No, it's open now.
Yeah,
Okay, and we need to finish 50. Have you finished? Maybe you can give the data information to him and then, yeah. So what's your name again? Sorry, I tried.
Brendan.
Brendan. Okay. Aaron.
Yeah.
And so what's your name?
Becca.
Rebecca. Rebecca or Becca?
Just Becca.
Just Becca. Okay. So I try to remember.
That's okay.
So this says X, Y, and I.
Yeah. Okay, Brendan. And then Becca finished the. This is 50, right? Okay.
This is the date that I use.
You can take your time, finish your 100.
I finished it though.
You finished it, okay. But the most
we throwing
important
that out
was the
anyway.
Yeah.
then you should basically see this. This is what opens
All days.
all day. Or no, go for the test. Or we go for each one.
That's what I.
Has three Q values. So that's good. You'll get 12.
Or maybe you can send an email to him and
Yeah, that might
copy
be.
paste.
I'll just copy and paste it from the other one. I just checked her values are good.
Okay. So it's the same? Okay. Where did you get this? I don't remember I sent this to you guys.
I did my homework.
Oh, good. I don't even know. I think I gave this to Min, and this only on my computer. Where did Min get the data? I don't know.
Where is yours?
Oh, so 100.
All right, we have different numbers.
Oh.
And you need to do all three groups. So like if you open Dave.
I only got
Dave. Okay.
Ah,
If I
yes.
do
Now
all
go to,
tests,
no, don't do that. Go to the first one.
I'm in Dave. I'm gonna open up one of my files. Desktop.
Oh, is this from
So you're doing 50?
No, 100.
100. Alright, so then select for this one, I'll load in the data. I'll select the function.
Yeah, so
I'll find my silly function because I saved it in this folder.
Yeah, very old version.
Yeah, I did the you fit it to the exponential function, right?
Brendan, what's your email?
I got your data.
Oh, okay.
Oh, it's because I didn't change this folder.
You did the exponential, right?
Yep.
Can I do all
No,
tests?
no,
Let me
no,
check.
no, no, just start with lowest.
Yeah, that's what I did.
Accept.
Yes,
I fit
and
it to
then
the current one. I
yes.
fit it to
Yeah,
all
and
of them.
select function.
So you have.
Oh, why do you fit it?
User function.
So I had to do everyone
And then you can
individually
the
because
user
I have to
function.
define the
Is
So yeah, I
exponential.
fit current and then I fit all. Because you want it to fit the one you're on, but then you want to fit it across the different Q values here.
Oh, so I
So
had to
then-
do each Q value individually because it wouldn't let me open up all of them.
Yeah. So no. So this is for concentration 0.05,
Yeah.
and 0.05 has embedded in it
Oh, I thought
three
this was
different
the
groups.
Q.
It is.
Yeah.
So the file that I uploaded was P06,
Uh-huh.
and so group 1 is this concentration. But then if I go to the second group, it has the second concentration in it. And if I go to the third group, it has the third one. So then if I did the same thing, but I picked 109, it's gonna pick up on the next concentration.
Oh, so this is
So that's where you get like the 0.56, 0.57, and then I just opened this one now. So that'll be the first
Okay.
one that loads in here once I do all this silly stuff.
Okay, let me see. Oh, 1, 2, 3. Oh, so
Yeah, so if you go back to 1,
so this is at
Yeah.
concentration 0.6.
You
So
can
we will
maybe
be
click
doing
this
this
one
one,
to
right?
save it.
Can
Oh,
I
so
quickly
this
go
is
to
not the.
so you're at 100, so
I'll be
concentration
there,
25. So yeah, if you go to your Dave and
Yeah,
you
So this
apply
is
Yeah. Just the
Q.
default value, just apply and
17.
dismiss.
so for Q17,
Yeah, then you can start fitting the current group.
Fit current.
Yes. And then you can say then the
Oh,
value
so
comes
this
out.
is changing. Oh, so this is Q17, but this is the constant.
yeah, those numbers.
Then
are
you
right.
can change the one.
Yeah.
There's 3 groups there.
Okay.
So is this the
And
this
this-
is the Q
the
value
different
right there,
Q
and this
values.
is
And I should make
and
it
what's
Excel.
17?
So yeah, so that's
like
it's like a rough
Brandon can collect all of them.
approximate of that one.
Uh-huh.
But if you go to group 2,
Uh-huh.
that'll be for
Yeah,
concentration 18673.
Oh, this is group 2.
Yeah, so then you'd fit all
Yeah,
of
yeah.
them. So fit current group and then fit all groups.
Okay.
Here.
Fit current. Okay.
And then you get like 1.24
Okay.
and 1.69.
Yeah, I doubt anyone here is working on Dave.
I see.
Yeah, that's a shame.
So you can try to finish the 10 milligram because
Yeah.
you need that concentration to make the files.
I
started.
so
So there's 2 groups.
I have this diffusion data.
Okay.
I put all this into text file.
Okay.
So if I just like copy this,
Well, what do you need to do in order Dave? If you want to use Dave to fit that, you have to make this. Make this. Let's say 10 concentration diffusion coefficient error bar. That's the little bit. You need to follow the syntax. So you just need to copy paste basically into that.
but it's different.
That's 0.1 inverse Armstrong. The Q value is the same. Q value is different.
So,
Q
so you're
value.
doing 10.
No,
Oh,
there's
so that's
0.1. That's this one. That's a 5.39, right? This is diffusion coefficient, and that's an error bar. That's for this Q value. Q value is 0.1.
For the error bar, we're just noting the absolute value, right?
Yeah.
So which is the actual?
So this is the result. This is when the error bar.
Yeah.
Yeah.
So for this concentration,
This is not a concentration. It's a Q value. This is Q value.
Oh,
This is
so-
concentration. This is concentration.
Okay.
Yeah, that's what I.
Yeah.
So this is Q, and then this is the. So this is 100 concentration. So that's
Yeah.
the one I've. Right.
So what is the diffusion coefficient? Or is that
Yeah,
one
this is diffusion coefficient and this is error bar.
Okay.
Why?
So mine is like a 0.1, right? 0.1 is 0.1065. That's this values. This is different concentrations.
So I want this information
Yeah, for that Q value.
for that. So I have to make that many text files.
I didn't find a better way to do it. Yes, sorry for that. Yeah.
No.
After finish that, you can send to everyone, maybe. But you need to put the concentration in the beginning. That's your X. And your diffusion coefficient is your Y. Then is your error bar. And save as a file name that you can recognize. I use the tab. I think maybe that's still okay. Save it to say that if David can read it.
So I'm gonna save this in
What's the depends on what you call.
data is
So I think that
oh, is that what these are?
so it's already loaded for you guys.
Let me investigate that. So who would you be? For 6, 13, for 6, 13.
Yes.
This is the.
Okay.
So like, there's like different groups, right? So there's 1,
Mhm.
and then 2.
Yeah, that's different Q
And
values.
there's a
Yeah.
different Q of
Yeah,
values.
yeah.
Okay. So like when we do the fitting,
Yeah, yeah.
you just do it.
Yeah,
You,
yeah. You need to restore. If you save it, you can restore the function over here.
I have trouble finding every time I save it. That's why I
Okay.
just.
Yeah.
Copy and paste.
It looks like they cannot do copy paste.
Okay. So now that I have a text file.
I didn't realize the mean copied everything from my drive. Okay.
Oh.
PP0 times exponential.
Yeah.
That is equal to the
0.
sorry.
Well, this one just usually for the tracking, but
Yeah.
most important the decay constant. That one gives you diffusion coefficient.
Okay. Yeah, so I don't need to worry about it.
Okay. So then, accept.
Because I put everything yesterday afternoon for that in the drive. I saw that he already uploaded. Probably he uploaded it last night and like uploaded all my analysis inside too.
Oh no, spoilers.
So then.
All right, so now-
favorite group.
Fit the current group first,
Okay.
then fit all the group.
I
Fit
keep
all the
zooming.
groups.
Oh, I'm back.
Okay.
So what do you do?
So
what's-
that does it when you say fit all groups. That does it for all.
All of
3?
them with same function. Then you
Okay.
can just change a different group. You can say that fitting value already here.
Right. Okay.
Okay.
And then, what goes on the file, the fitting results file right here?
Yeah.
Is you choose the constant or whatever.
The
so
decay constant.
decay constant.
Yeah, that's the constant you need to put there.
For so you have to do
For the
it for
different
all
equipment.
three
For each group and each
group.
folder.
Yeah, for
Okay.
each configuration.
Oh, I see.
So how do I
It has a four
Oh.
configurations.
make Dave do this? So I opened.
You need to define linear function to fit that.
All right, select user function. Is there already a linear function?
No, you have to define that. I'll show you how to define that.
I guess if I do this.
It's very easy because I already defined that. They store it, and then they should have a linear function there. It's very simple.
So why are we fitting the current group and then doing all groups? Can't I just
Yeah.
do all groups on the first try?
It's just like they have different files, but you can do the both. Usually, I just don't know. That sometimes David they may have the issue. If you keep fitting all group, it works. Go ahead, do it.
Okay, I see. Yeah.
Oh, okay. Those are. I was just missing some of the Q.
All right, so I
I
have
get.
that expression. I saved it.
Yeah, but then you need to fit it.
So I fit group and fit.
But then you need to you want to exclude this one.
I'm sure.
In order to go to File, Preference,
It won't work.
and then the fitting range. You put maybe upper
Yeah, it
limit
doesn't
to
like-
60 or something like that.
The run.
Do something greater than my middle point.
Yeah. Oh no, they didn't move it. Should do it again.
Neither does it. I just
You don't
restarted.
accept it. 60 and apply.
Magic.
Okay,
I guess
then good.
Windows-
Then it's good.
Just for this.
Now
I
you can
get.
fit.
I get.
Yeah. Now you get the magic number.
It's still the P1 value.
Well, it depends on how you type the parameter, right? The intercept is the one you are interested in.
Yeah.
So you think about which one is the right one. Remember that. Okay, Roshin already read it there. The intercept is what you are interested in. Intercept means the x go to 0, right?
Yeah.
And which one give you a result for intercept? That's 0, right? That's, yeah. Yes. That's why I let them take time to analyze all the data because they need to have a feeling for that.
So now that I have this,
Then you need to put it for different Q. That's the finally infinite dilution diffusion coefficient. Then you need to so if you go to the plot, I have a somewhere. Okay, you didn't have it here. So I plotted you can make a new tab and then can plot them out.
Oh, this is.
At the different Q value, now you have infinite dilution, right? For each Q value, you have done it. So you can copy that data.
so
there.
what did I just open? I opened 0.05. Oh, yeah. Oh, was that? Is it these things?
What do you mean? What's your question? First. Because what we are trying to do is get diffusion coefficient at different Q values and infinite dilution. This is new data. So it's
So I fill that in here.
okay, yeah, you can fill it anywhere. Yeah.
Okay. So then this is just my Q value.
Yeah.
Singular data point.
Yeah.
And then what would this column be? Or is this just the equation? This looks like the. So I need my P0, but I also need the error.
Yeah.
So I load data from 105, 106. My boundaries are good. Restore expression. Desktop. Is this one excluded? Technically.
Nope. If you see this one, that shows the ending point. Yeah, that's the annoying part. Every time you load it, you need to redo it.
Okay, that looks better. So when do I ever have to move the initial, like the lower limit?
No,
Was that fine?
that's included.
Oh.
So Brandon is trying to move into next step, get all the concentrations, and start fitting the data, get the infinite dilute concentration diffusion coefficient.
Yeah, so I get our fitting results, right? And then we get our Q value, different concentration Q value coefficients for diffusion. And then I take these, break them down into these little text files, and just collimate them. And then I import this to Dave here. So I would just like data, load that, and then I would just pick 0.07, which is what this one is. I get my new function, which is the linear one, which looks like this. It's also on the whiteboard behind me. And then I save that, apply it. I already moved this, but typically it's not that far over. So you go to File, Preferences. It'll normally be at 100. So then it's including this point, but you want to move it over. So I've just been putting it at 60. So then it just has these two central points in, or
three left.
I don't know why it disappears sometimes. But yeah, I'll move this back to 60. I'll apply it. I already made it linear, so then I'm going to fit to my current group, fit all groups. And then this is our
diffusion coefficient.
Yeah.
Well, I would not put D0 Q. I mean, and Q dependence, you will see that they are different at different values. Yeah, that's right.
And I've been putting them in here. In case anyone was curious.
So I'll send the simulation results to you guys too. So Brandon, what's your email?
BBK 5119.
BBK
119
5119
at psu.edu. My computer's gonna crash.
What are you waiting for?
Me?
I finished the 10, but I think the 10 is already there.
Well, I'll look at them. Is this what yours?
It's the 10 because I.
Is this what your 10s look like?
It's in the pen.
Huh?
It's in the pen.
Oh boy.
All right, I'm gonna
Yeah,
discount
that's
that.
how it looks like. 1.28.
Yeah.
0.18. Yeah, that's how it looks like.
Which data
Three.
points are you exporting to TXT file?
The diffusion ones. Here.
And where did you get diffusion from?
He already had a template set up that would just read our fitting results and apply this to them.
So the diffusion coefficient, just like I showed you, the what did you get it? A?
A particular Q, we get it
A equal
at infinite, and now we probably how that looks as a particular Q. So that's like a Saturn.
So what template is doing that, just divide by Q squared. And of course, when they read that, they read the time, not in another second, they read the seconds. They have to convert that to the nanosecond. So there's some unit conversion built into that Excel file.
No.
They're all curves. They're all
So to get the fit the concentration dependence now. So once everyone get it, so then while he's working on it, I just sent the email to you for the normalized diffusion coefficient from simulation, and then you can plot your result compared to that. But the simulation, the rigid body simulation, it's not does not include internal motions. So we'll talk about that later. Okay.
So it assumes a sphere.
No, it's not sphere.
Rigid
It's
body.
they read the PDB and run the DPD simulation, but then it's the same protein shape, but they just do not have this internal motion.
Okay.
And so the difference presumably is due to the internal motion. Yes, right.
Can I ask you a question?
Yes.
I guess I'm confused on like why were we finding these then?
All of the different.
This information, the P1s.
So you were finding the diffusions, right?
This?
Oh, which one?
Wait, from earlier?
Yeah. So what does this information tell us?
We're extrapolating to infinitely dilute.
Oh, which part of information? Oh, this one. That's a decay constant, right?
I'm not sure. That I thought that this was something different. So that's where I'm confused.
So P of 1 is the exponent, which is basically related to the diffusion coefficient. And so you get the diffusion coefficients at each Q for a single concentration of yours now. But then he's gathered all the data for all the concentrations. Now for a single Q, you take the diffusion coefficient as a function of concentration, and you do this extrapolation to get the D naughts.
Can I have someone walk me through that process? Because I have a hard time.
So first, this decay constant we got, right?
This?
Do you know what its value is? Do you know what that value is first?
No.
Okay. So you work on which concentration? 25 milligrams per milliliter, right?
I did 50.
You did 50.
Yeah.
So that's a decay constant you suppose you have for 50. Yeah. That's a decay constant. That's the P1 we're talking about. That's the kind of, and then the next column associated with is the error bar from the 50. And this one essentially is the decay constant we're talking about. That's equal to Q squared times the diffusion coefficient. So yeah. So by taking your decay constant divided by Q squared, that can get your effective diffusion coefficient.
So this decay constant is equal to Q squared. So if that helps. So then we're getting that value because once we have a value, we can divide by Q squared. And then we get the And if you think about diffusion analysis, basically, if you think about diffusion as so expensive layer of that data.
So it's okay.
Yeah.
So we'll talk about that. Or when we finish that, and then we'll talk about the theory behind of this. But you know at least what we get now. That's decay constant from exponential decay fitting. And by divide by Q squared, we try to get diffusion coefficient. For single protein, it's a spherical particle. That's the diffusion coefficient that you will get in the solution. How fast they move in the solution, basically. Okay.
He has that matrix.
Oh, it switches.
Since Q corresponds to landscape, we can look at how fast whatever part of the solution is moving in different landscapes. So like for me, if I plot diffusion versus Q, I'm thinking